Hello students, welcome back. So in the previous lecture we have completed the complete phenol chapter. So we have basically completed the alcohol chapter, we have completed alkyl halides. So the next very important chapter is aldehydes and ketones. Now aldehyde and ketones is a very important chapter because there are many reactions in this particular chapter that finds a direct application in JEE paper. So make sure that you are doing this topic as well at the top notch and you are solving a lot of content, you are understanding all the reaction and you are doing a lot of good level problem solving which will help you in understanding these reactions and understanding this particular chapter. So let's get started. So in today's lecture we are going to talk about preparation of aldehydes and ketones. So the first preparation that we are going to talk about is the preparation from alkanes. So when you heat an alkane in air along with MnO₂O₃, MnO₂O₃ is basically molybdenum trioxide. So this acts as a catalyst and this converts the alkane into a aldehyde. So alkanes are converted into aldehyde when you do a partial combustion in presence of MnO₂O₃. The next preparation is from alkene. Now we know that we can prepare an aldehyde or ketone from an alkene through a ozonolysis reaction. So we say that alkenes can be converted directly into aldehydes or ketones by reductive ozonolysis. I hope you remember this particular reaction. This reaction you might have done in your 11th class. So when you treat an alkene with ozone and in the second step you add zinc and water. So that is called as a reductive ozonolysis. So that is basically called as a reductive ozonolysis. So taking ozone in the first step, the solvent generally used here is dichloromethane. And again we maintain a very low temperature like minus 78 degrees Celsius, and the second step we take zinc and water, or we can take zinc acetic acid, we can take DMS which is dimethyl sulfur, or we can take triphenyl phosphine. So in this case reductive ozonolysis happens. So I am not going to discuss the mechanism of this reaction, I am just going to tell you the shortcut way to understand this reaction. Now what we can do over here is, we can break this double bond. Whenever we are doing an ozonolysis, just break the double bond and against this double bond put an oxygen. So put an oxygen over here, put an oxygen over here and just cleave this double bond. So this oxygen will get attached to this carbon and will form a aldehyde. Similarly this oxygen will get attached to this carbon and it will form a aldehyde. So once you add zinc, once you add ozone to an alkene and in second step you add zinc water or zinc acetic acid or dimethyl sulfur, in that case the double bond cleaves and we get the molecule of aldehyde. This reaction is known as a reductive ozonolysis. Okay, so I am not going to discuss the mechanism. I hope you know the mechanism, Crick mechanism that happens in this reaction. So let us take some question now. So suppose we are having a molecule of benzene and we are doing a ozonolysis. We are doing a reductive ozonolysis. So in reductive ozonolysis first we add ozone and in second step we add zinc and water. So just write the product and then suppose we are taking this molecule and we are again carrying out a reductive ozonolysis. So these are few examples of reductive ozonolysis. Just write the product. So what is going to happen in this case is, just you have to break the double bond. So just break all the double bonds. So this is one double bond, this is the other double bond, this is the other double bond. Put a oxygen over here, 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 oxygen over here and oxygen over here. Now when you break this bond, we form CHO. Okay, you can see that we will form this is a carbon, there is a hydrogen over there, so it will form CHO. When you break this bond, this will also form CHO, and once you break this bond, you will also form CHO. In this case, we are going to form 3 moles of glyoxal. This molecule is basically called as glyoxal. Now suppose we are taken this molecule and we are carrying out a reductive ozonolysis. So what will happen? This double bond will cleave, this double bond will break. Similarly, this double bond would also break. So in this case, we'll form a ketone. Just put an oxygen over here, put an oxygen over here. So this will form a ketone. Oxygen will come over here against the double bond. Hydrogen is there, so it forms an aldehyde. Similarly, when you do the ozonolysis of this molecule, you will form a ketone over here and an aldehyde over here. Okay, so this is the product that we are going to form. So this is an example of reductive ozonolysis. So let us just also cover the oxidative ozonolysis as well. Now what happens in an oxidative ozonolysis is oxidation happens of aldehyde. So in case of any aldehydes being formed, they will basically oxidize into carboxylic acid. So we say that in oxidative ozonolysis, if any aldehyde is formed during the ozonolysis reaction, now we know that in the aldehyde this hydrogen is oxidizable. So this will get oxidized and will convert into a carboxylic acid. Similarly, if we generate a formaldehyde through a ozonolysis reaction, then again this is going to get oxidized. Aldehydes are generally easily oxidized into carboxylic acid as they have oxidizable hydrogen. So the hydrogen that is directly attached to the aldehyde group would get oxidized. So we'll form a formic acid over here. Now once you have formed the acid over here, you can see that there is still a aldehydic type of group that is left in the molecule. So in this case again, this particular segment will also undergo oxidation. So again it will form a carbonic acid. So in this case we form a carbonic acid. Carbonic acids are highly unstable, it will change into CO2 and water. So just you have to remember this point, in oxidative ozonolysis, if any aldehydes are formed, they will be oxidized into acids. If formaldehyde is formed, they will be oxidized into CO2. So let us take some example now. Suppose we are having this molecule, suppose we are having this alkene and we are treating it with ozone and we are not adding zinc. So whenever zinc is not added in the mixture, it will indicate that we have to carry out a oxidative ozonolysis. Once you have added ozone and in the second step you are adding zinc, it will indicate that you have to do a reductive ozonolysis. Either you add zinc or you add dimethyl sulfur. Either you add zinc or you add dimethyl sulfur. Because we have not added zinc over here, so we will carry out the ozonolysis in a oxidative manner. So you have to just break the double bond, put an oxygen over here, so it will form a ketone and this will form a aldehyde over here. So a ketone and aldehydes are formed in this case, right? Now once this aldehyde is formed, we know that they will get oxidized into carboxylic acid. So in this case, we will form a molecule of carboxylic acid and a molecule of ketone. Ketones do not have oxidizable hydrogen, so they don't get oxidized under ozonolysis condition. Now suppose we are having an alkene like this. To this we add ozone, and in second step if we are adding zinc, then we have to take a strong oxidizing agent like H2O2. So in oxidative ozonolysis we add ozone and in second step we don't add zinc. Then we have to carry out a oxidative ozonolysis. Otherwise we say that if we are adding zinc to it, we have to add a oxidizing agent, a strong oxidizing agent like hydrogen peroxide that would oxidize the aldehydes into carboxylic acid. Okay, so when you are adding zinc, then you have to take H2O2 along with it. So we have to break this bond, put oxygen over here, put oxygen over here. Now you can see that this will convert into a aldehyde. So this aldehyde will oxidize into acid and this will generate a formaldehyde. Formaldehyde generally oxidizes into CO2. So we are going to get this as the product. Okay. So the major difference between reductive ozonolysis and oxidative ozonolysis is, in reductive ozonolysis we take zinc in the second step along with water, or we take dimethyl sulfur. Whereas in oxidative ozonolysis, in the first step we are taking ozone, and in the second step zinc would be absent, so that oxidative ozonolysis can happen. But if you are taking zinc in the second step, then you have to take a strong oxidizing agent like H2O2. Okay, so I hope this is clear to you. Ketones are not oxidized as they do not have oxidizable hydrogen. We can also carry out oxidation of alkenes through alkaline KMnO₄. Okay. So suppose we are having this alkene, and we have added alkaline KMnO₄ to it. So we have added KMnO₄, OH negative, and in second step we have added H3O plus. We are basically hydrolyzing it. So this reaction is same as that of oxidative ozonolysis. Just break the double bond. So just break the double bond, put oxygen over here, put oxygen over here. So this will convert into a ketone, and we'll get a aldehyde over here. But because we are using a strong oxidizing agent, so aldehyde will oxidize into carboxylic acid. So in this case, we are going to form carboxylic acid. So we can also carry out oxidation of alkenes through alkaline KMnO₄. The reaction is similar to that of oxidative ozonolysis. Okay, so these are the reactions that we often cover in alkene chapter, that is the part of hydrocarbon. So I hope after seeing this reaction, all those concepts are reappearing inside you. The next preparation from alkenes could be done by causing a dihydroxylation and then carrying out the oxidation of the diols through HiO4 and lead tetraacetate. Okay. So again, this is a reaction of alkenes. So first we have to carry out a dihydroxylation. So first we will carry out a dihydroxylation. So what we will do over here is, we will add osmium tetraoxide, and in second step we add sodium hydrogen sulfide, or we will add Bayer's reagent. Bayer's reagent is basically cold alkaline KMnO₄. So this is basically cold alkaline KMnO₄. Okay. So we are having a double bond, and to this we add osmium tetraoxide NaHSO3, or we add Bayer's reagent. We know that both these reagent causes a dihydroxylation. So 2H will be attaching to the carbon and they add in a syn fashion. So in this case we get a diol. So we form a diol, and both the OH are basically getting attached to the carbon from the same side. So in this case we say that syn diols are formed. So osmium tetraoxide and Bayer's reagent is basically used to convert an alkene into a syn diol. Now once we have got a syn diol or we have got a vicinal diol, we can oxidize them using lead tetraacetate or periodic acid. This we have discussed in the chapter of alcohols. We generally say that whenever we are having diols, 1, 2 diols or vicinal diols, they will be oxidized by HiO4. So basically you have to break this bond. Now once you break this bond, you just put a OH over here and a OH over here. So this will oxidize into a ketone and this will oxidize into a aldehyde. So we get a molecule of aldehyde and ketone. Now you can see that all the reactions that we are doing are mostly repetitive reactions that are coming from either hydrocarbon or alcohols or alkyl halides. Okay. So just make sure that when these reactions appear, you understand these reactions, you know the mechanisms of these reactions, and you are able to think of these possibilities very quickly. And that is how organic becomes very progressive. That is how you actually become successful in creating a good reaction database. So everything is connected in organic chemistry, right from the start till the end, everything is connected. So you have to just keep on looking for that connection. You should always establish a connection between the previous chapter and the chapter you are doing. That actually helps you a lot. Next we can do is the preparation from alkynes. Now we know that upon acidic hydration of alkynes, we generally get ketones. So again this is the reaction from alkyne. Now this reaction is known as Kirchhoff's reaction. So this is basically known as Kirchhoff's reaction. So when you do an acidic hydration, when you add a water to an alkyne molecule, first we form a enol. This enol tautomerizes because enols are unstable. So they will tautomerize. So this hydrogen will migrate towards the carbon and we'll get a ketone. So upon acidic hydration of alkynes, either we get a ketone or a aldehyde. Generally we say that the addition reactions on alkynes are not done directly by addition of nucleophile, because if nucleophiles are added, nucleophile will try to come and attack at the alkyne carbon, because there is a triple bond at the alkyne carbon. So obviously there is a high pi electron density. So when the nucleophile approaches the alkyne, the nucleophile will be repelled by the pi electron density of the alkyne. So what we do is we generally use heavy metals in the reaction. So we use Hg2+. So Hg2+ first coordinates with the pi bond. So this coordinates with the pi bond. Pi electrons are donated into the empty orbital of Hg and it basically forms a cyclic intermediate. It basically forms a cyclic intermediate. Okay, so it basically forms a cyclic intermediate. Now because there is a formation of 3-membered rings, obviously this ring will break. It will break from here because the carbocation formed at this particular carbon would be more stable, as alkyl group would be releasing electron through inductive and hyperconjugation. So carbocation would be formed at this carbon. So as the carbocation is formed, water attacks on the back side. So it forms a molecule like this. Okay. Now what happens over here is sulfate ion basically goes and attacks at the Hg2+, Hg, and it basically abstracts Hg and we form obviously there is H+, so this negative charge would get protonated. I think I made this wrong. This is only one hydrogen. So basically there would be 2 hydrogen over here. Okay, so we get this particular molecule. Now this is enol. We know that enols are unstable, so they will tautomerize. So this is the mechanism that you have to follow. But just remember that this is basically Markovnikov addition of water. So when you add water to an alkyne, we add water through HgSO4 and dilute H2SO4. So we add to an alkyne, we add HgSO4 and dilute H2SO4. So Markovnikov addition of water takes place. We form a enol that tautomerizes to give us ketone. Okay, so I hope this is clear to you. So let us take some reactions. Let us take some examples on this. So suppose we are having these molecules. So we are having a ethyne and we are carrying out a hydration. Suppose we are having propyne So just write the product of these reactions. Just write the product of these reactions. Okay, just write the product of these reactions. So in all these reactions we have to carry out hydration, acidic hydration. So water will be added. So you have to add water in a Markovnikov fashion. So in this case, H will get attached over here, OH gets attached over here. So we'll form this molecule. So this enol is unstable, this will tautomerize, so hydrogen will shift over here and we are going to form a aldehyde. Similarly, there is a triple bond over here, we add again water to it. So this is again a Markovnikov addition, so positive part of the reagent will attach to that carbon which has more hydrogen. Carbocation will be formed at this carbon, okay, because methyl will release electron through hyperconjugation and stabilize the carbocation. Again this is a enol, this will tautomerize, so we will get a ketone over here. Now in this case, when you take 2-butyne and you add HgSO4, H2SO4, so this is again addition of water. Because this is a symmetrical alkyne, you can add water between any carbon, they will lead to the same product. Okay? In this case, when you add water, so H will get attached over here, carbocation will be formed over here because it will be stabilized through resonance of benzene ring. So in this case, hydrogen will be attached to this carbon and OH will be attached to the benzyl carbon and will form this product. Again this is a enol which is highly unstable, so this will tautomerize and will get this molecule. Now when we add water to this particular alkyne, so in this case carbocation will be formed over here. It is not forming exactly a carbocation, first a 3-membered cyclic ring is formed which is breaking and giving a partial carbocation. So partial carbocation at this carbocation would be, at this carbon would be more stable as this is having more number of alpha hydrogen. So this carbocation will be more stabilized. If a carbocation is formed over here, it will have only 2 alpha hydrogen. Because it is having 3 alpha hydrogen, so this carbocation is more stabilized. So OH will be attacking at this carbon and will form this particular molecule. Now you can do the tautomerization and we will form this as the product. Okay, so we will form this as the product. So I hope this is clear to everyone. The next reaction that we can do on alkynes is the reductive ozonolysis. So when we do a reductive ozonolysis on an alkyne, so just break the double bond. Just the way we are doing in ozonolysis, we have to break the double bond. When you break the double bond, there is one bond that is still left. Add oxygen on this, so we will form a diketo. If you take this molecule and carry out a reductive ozonolysis, then again you have to break the double bond, add a double bond over here, add a double bond over here, and we will get this molecule, right? But when we are carrying out a oxidative ozonolysis of this molecule, so in oxidative ozonolysis, the entire triple bond will break. This carbon will oxidize into carboxylic acid and this carbon will also oxidize into a formic acid. Now formic acid will further oxidize into carbonic acid and we will get CO2 as the product. We can also do the oxidation with cold alkaline KMnO₄. So if on a triple bond, if on an alkyne, we add cold alkaline KMnO₄, we are going to get a 1,2-diketo. Okay, so again the same mechanism is operating, just add a OH and then you will tautomerize it. So just add 2 OH and then tautomerize them. So you will form a diketo molecule. The next reaction is the preparation of aldehydes and ketones from alkyl halides. Now alkyl halides can be directly converted into a aldehyde or a ketone through a very important reaction, that is Kornblum oxidation. Now what we do in Kornblum oxidation is, we take an alkyl halide, we react it with DMSO, dimethyl sulfoxide, in presence of a base at a very low temperature like -78 degrees Celsius, and it converts into a ketone or a aldehyde. So this reaction is somehow similar to the Swan oxidation that we did in alcohol. Swan oxidation was basically used to convert a 1 degree alcohol into aldehyde and a 2 degree alcohol into a ketone. So let us just discuss the mechanism of this reaction. So we are having a alkyl halide. So suppose we are having a alkyl halide something like this. So we are having a 1 degree alkyl halide and we are adding DMSO to it. So we know that these pi electrons would polarize on oxygen, oxygen will have a negative charge. So this will go and attack at the carbon, Cl will come out and we are going to form this particular molecule. Now we have taken a base. Generally the base taken over here is triethylamine. So this is a strong base, so this will go and abstract this hydrogen. Now once this hydrogen is abstracted, it will push its electron and the living group will go out, and we are going to form a aldehyde and dimethyl sulfur. You can see that this reaction is exactly like Swern oxidation. So if you take a 2 degree alkyl halide, suppose we are taking a 2 degree alkyl halide and we react it with DMSO, and in second step we add triethylamine. Temperature maintained is generally very low, so this will first attack, so oxygen will get attached, the base will abstract this hydrogen, it will push the electron and dimethyl sulfur would go out as a living group and we will form a ketone in this case. So this is the reaction. This reaction is known as Kornblum oxidation. So Kornblum oxidation basically oxidizes a 1 degree alkyl halide into aldehyde and a 2 degree alkyl halide into a ketone. Okay, so I hope this is clear to you. This is exactly similar to Swern oxidation. Now we can also carry out the preparation of aldehydes and ketones from alcohols. Now we have already studied that oxidation of alcohols gives us aldehydes or ketone. So basically it is the oxidation reaction that we need to study again. So again I am not going to revisit it. I hope you have memorized all the oxidizing agent. So 1 degree alcohol with mild oxidizing agent oxidizes into aldehyde. Mild oxidizing agents were PCC, pyridinium chlorochromate, PDC, pyridinium dichromate, Collins reagent, CrO₃ in acetone, then copper heat, X2NaOH. So these were the mild oxidizing agent that were converting 1 degree alcohol into aldehyde. Similarly, you can carry out a Swern oxidation, you can react it with ferric ammonium nitrate, all of them converts 1 degree alcohol into a aldehyde. But with strong oxidizing agent, 1 degree alcohol converts into carboxylic acid. Now if I take a 2 degree alcohol and treat it with any oxidizing agent, be it a mild oxidizing agent or a strong oxidizing agent, both these oxidizing agent will convert 2 degree alcohol into a ketone. Strong oxidizing agent like alkaline KMnO₄ or potassium dichromate or chromic acid or Collins reagent, they all will convert Jones reagent. Collins is basically a mild oxidizing agent. So 2 degree alcohols with any oxidizing agent converts into a ketone. Now if we talk about 3 degree alcohol, 3 degree alcohol do not have oxidizable hydrogen, so they do not oxidize under normal conditions and we don't get any oxidized product over here. Okay, so I hope this is clear to you. Next reaction is from carboxylic acid. We can carry out a dry distillation of calcium salt of carboxylic acid. So we can carry out a dry distillation of calcium salt of carboxylic acid. So if you take any, let me first show you the reaction. So suppose you are having a carboxylate ion. Okay, so this is basically calcium salt of carboxylate ion. So when you heat it, so this is basically dry distillation. So in this case CaCO3 is removed, so calcium carbonate goes out and this R group will basically get attached to this carbonyl carbon and we will form a ketone in this case. So this reaction is known as dry distillation of calcium salt. Now we can also take two different molecules and carry out the dry distillation. So suppose we have taken this molecule and we have taken this molecule. So this is basically calcium formate. As you can see that this is a formic acid. So this is basically calcium formate and you are heating with say R is methyl, so this is basically calcium acetate. Now when you heat it, there will be two kinds of product formed. One is the self product, other is the cross product. So if we talk about the self product, if you heat it, calcium carbonate will go out from here, this R group will get attached over here and we'll form a ketone. Similarly, if you take calcium formate and heat it, so calcium carbonate will go from here and hydrogen will get attached over here. So it will form a formaldehyde. So these would result into the self product. So these are the self product that would be formed. Now there could be a cross product as well. So this calcium carbonate is going out. Similarly, this calcium carbonate is going out on dry distillation. So this R groups get attached to this carbonyl carbon. This RCHO, RC double bond O groups gets attached to this hydrogen. So we are basically going to form a aldehyde in that case. So we form 2 moles of aldehyde. So this is our cross product that can be obtained. Okay, so this reaction is known as dry distillation of calcium salt of carboxylic acid. So again we are having calcium salt heated, we will get calcium carbonate and a ketone. Similarly, we can also carry out the reaction with acid. So when you take carboxylic acid and you heat it with MnO at 300 degrees Celsius, take a carboxylic acid, heat it with MnO at 300 degrees Celsius. So in this case CO2 is evolved from here and water goes out from here, and we are going to form acetone. Okay, we form acetone in this particular case. So when you heat a acid in presence of MnO, so CO2 is expelled out, water is expelled out, and this group gets attached to gets attached to this carbonyl carbon, and we form a acetone molecule. Now we can also prepare carboxylic acid. We can also prepare aldehyde ketones from carboxylic acid by reaction with alkyl lithium. Now this is a very important reaction because this contradicts the basic knowledge of Grignard reagent. Now we know that when you treat a carboxylic acid with a Grignard reagent, so carboxylic acid reacts with Grignard reagent, so this CH3 negative would abstract a hydrogen and form a methane gas. So we form a carboxylate ion and a methane gas. Now we know that carboxylate ion is stabilized through resonance and it is not attacked by another molecule of Grignard reagent. So basically we are reacting carboxylic acid with a organometallic compound. But when I react with RLI, with excess of RLI, and I hydrolyze it, I observe that a ketone molecule is being formed. Now let us understand why this reaction is happening, because we know that this reaction was not happening because carboxylate ion was highly stable due to equivalent resonating structure, due to which Grignard reagent was not able to attack on carboxylate ion. But once we have taken an RLI, so in RLI we are having a carbon with a negative charge, so this will basically abstract the hydrogen. So these electrons are pushed on the oxygen, so we form a carboxylate ion. And now to this O negative, a lithium plus would get attached. Now we know that lithium plus is a small size cation. Because it is a small size cation, so this will polarize oxygen. So this polarizes oxygen. So this attracts the oxygen more towards itself because it is a small size cation. Due to this strong attraction, this O negative won't be able to enter into resonance with this C double bond O. Because the negative charge is polarized by the lithium plus ion, so this negative charge will not be easily available to enter into resonance, due to which another molecule of RLI can attack on this particular carboxylate ion. Okay, so this RLI will go and attack at this carbon. This is having a negative charge. These pi electrons are polarized. So in this case, we are going to form RCOLI, OLI, R. Then we'll hydrolyze them. So when we hydrolyze, we form a diol. Now we know that diols are unstable. So this will liberate water and change into a ketone. So you can see that in the first place, what is happening is a acid-base reaction. So basically we are forming a RH and a carboxylate ion, but because lithium plus was small size cation, it was able to polarize oxygen effectively, due to which the resonance between O negative and C double bond O was disturbed, due to which another molecule of RLI was able to attack at the carbonyl carbon, which is not possible over here. And we formed a diol, which will eventually give us a ketone molecule. So this is how we can prepare from carboxylic acid using alkyl lithium. Now the next reaction is known as Rosenmund reaction. So we take a acyl chloride and we react it with, you can guess this reagent, this is Lindlar's catalyst. So we react acyl chloride with a Lindlar's catalyst and we get a aldehyde. Lindlar's catalyst is basically hydrogen, palladium, barium sulfate, and we add quinolin. Quinolin basically poisons the catalytic activity of hydrogen. So quinolin basically acts as a poison. Because hydrogen metal is a very strong reducing agent, so obviously it will reduce this acyl chloride into a 1 degree alcohol. So this reaction won't stop at acyl chloride because this is a strong reducing agent. So first hydrogen will get attached, it will form an aldehyde, then again hydrogen metal can reduce C double bond O into a alcohol. But since you have taken quinolin along with this, quinolin basically poisons the activity, it poisons the mixture and it decreases the reducing power of hydrogen palladium, due to which reaction stops at aldehyde and it does not get further converted into a alcohol. Okay, so just remember this reaction, these are very important reaction. Similarly, Lindlar's catalyst is also used to carry out hydrogenation of a triple bond. If we are carrying a hydrogenation of triple bond through hydrogen metal, it will convert it into a alkane. But once you have added Lindlar's catalyst, which is poisoned by quinolin, due to which the catalytic activity is reduced, due to which this alkyne will only get converted into a alkene. So we say that this is the cis addition of hydrogen and we form a cis alkene in that case. Okay, so let us just check out one reaction. So suppose we are having, say, this kind of molecule, and to this molecule we have added Lindlar's catalyst. So Lindlar's catalyst will basically convert triple bond alkyne into a cis alkene. So this converts into a cis alkene and acyl chloride would convert into a aldehyde. So this is the product that we are going to get in this particular reaction. So this reaction is known as Rosenmund reaction. Next is preparation of aldehydes and ketones through organometallic reagents. Okay. So if we consider, say, RCOCl, if we react RCOCl through to RuCuLi, RuCuLi is basically dialkyl lithium cuprate. So in this case there is a R negative that is generated over here. This goes and attack at this carbonyl carbon, pi electrons are polarized, O negative will push the electron and Cl will go out and will form a ketone in this case. Now this reaction stops as ketone only. Now this does not further react with R negative to form a 3 degree alcohol. So if you react acyl chloride with R2CuLi, you will get a ketone. Similarly, if you take RC triple bond N and you react it with a Grignard reagent. Okay, I hope you remember all these reactions we have already covered. So this is just a quick revision of what we have done in reagent and mechanism and alkyl halide. So this basically converts RCN into a ketone molecule. Okay, but if you are reacting with ester, so we have to control this reaction. So if you add one equivalent of RMgX, in that case we form a ketone, but if it is in slight excess also, this will quickly react with Grignard reagent and undergo acidic workup to form a 3 degree alcohol. So this step is, this reaction is basically not chosen to get a ketone. So these are the few reactions with organometallic compound. Now we can also carry out the preparation of aldehydes and ketone through reduction. So if we are having a acyl chloride and we react it with dibyl H. Dibyl H is basically di-isobutyl aluminum hydride. Okay, so this is di-isobutyl aluminum hydride. Okay, we generally maintain low temperature with dibyl H, something like minus 78 degrees Celsius. So in this case, acyl chloride changes into a aldehyde. Similarly, if you take a ester and you react with same dibyl H, same condition, you get again a aldehyde. Similarly, if you take a cyanide or a nitrile, you react with dibyl H, again you get a molecule of aldehyde. Okay. Now what exactly is happening over here is, let us just discuss that. So when we were reacting say acyl chloride ester or a ester with lithium aluminum hydride. So lithium aluminum hydride was a strong reducing agent. So this was sending its hydride ion to the carbonyl carbon. So again this intermediate tetrahedral intermediate was formed. So O negative was pushing the electron, Cl was going out. So we are forming a aldehyde in that case. So first aldehyde was formed, then because a carbonyl group is generated, it will be attacked by another molecule of lithium aluminum hydride and it will form a 1 degree alcohol. So if you add lithium aluminum hydride to all these molecules, this will get converted into a 1 degree alcohol. This will also get converted into a 1 degree alcohol and this will convert into a amine. So this will convert into amine, they will not convert into aldehyde. So what exactly dibyl H is doing? If you look at the structure of dibyl H, it is basically diisobutyl lithium aluminum hydride. So its structure is something like this. Now you can see that this is highly sterically hindered. Because of its highly steric crowding, it only provides one hydride ion. So this will provide only one hydride ion and it will convert into aldehyde. It will provide only one hydride ion and it will convert into a aldehyde. Similarly, with cyanides, it will provide one hydride ion and it will convert into a imine RCH double bond NH. And then in the second step, you do a hydrolysis. Hydrolysis of imines give us aldehyde. So we form a aldehyde in that case. Okay, just remember that dibyl H do not affect carboxylic acids. So carboxylic acids are not affected by dibyl H. Okay, so dibyl H is very selective reducing agent. It is basically due to its high steric crowding that it is not able to reduce acyl chloride ester or amines or cyanides further, and they basically stop the reaction at aldehyde. Okay, so I hope this is clear to you. Next reaction is a Stephens reaction. So in a Stephens reaction, what we do is we add SnCl2 and HCl to a cyanide. So basically hydrogen addition happens over here. So we form a imine. Now we know that imines undergo hydrolysis, so they will hydrolyze and we will form a aldehyde molecule. So first we form a imine which hydrolyzes to give us aldehyde. Similarly, suppose you are having this molecule, you can see that we are having a CN and you add SnCl to HCl, so CN will get converted into CHO. So Stephens reaction is used to convert CN directly into CHO. You need to remember all the reactions, particularly well just upon looking at the reaction, you should be able to predict what is the product now. Next reaction is a Itard reaction. So in Itard reaction, we generally say that toluene is directly converted into a benzaldehyde. So you react toluene with CrO2 Cl2, which is chromyl chloride. So you react toluene with chromyl chloride along with carbon disulfide as the solvent. Just heat the mixture, you will get a benzaldehyde. Now this reaction mechanism has been given in different manner. Some scientists have said that this happens through a radical mechanism. Some have given a separate ene-ine type of mechanism, which is also a sigmatropic mechanism. So we are not going to enter into those mechanisms because they are generally not asked. So if you want, you can refer any good book and you can see the mechanism, but we are not going to discuss because that is not the part of JEE. So toluene on reacting with CrO2 Cl2 in presence of carbon disulfide forms a chromium complex which upon hydrolysis gives us benzaldehyde. Okay, so just remember these reactions, these are highly important reactions because there will be questions on conversions. So you should be able to understand the specific action of the reagent. You should know which reagent will directly convert a given molecule into a desired product. So whenever we are having a toluene, just react it with chromyl chloride in presence of carbon disulfide as a solvent, we will get a benzaldehyde molecule. Similarly, if we take a toluene and we add chromic oxide to it, chromic trioxide to it, along with acidic anhydride, and again we hydrolyze, so in this case we also form a benzaldehyde. Okay, so we form benzaldehyde in this case as well. Now what happens in this reaction is, first the toluene reacts with acidic anhydride and forms a ester. Now this ester upon hydrolysis, we know that ester upon hydrolysis will give us alcohol, so it forms a geminal diol which loses the water to form a benzaldehyde molecule. So once you have taken toluene, add CrO₃ in presence of acidic anhydride and just hydrolyze it. So we get a molecule of benzaldehyde. But if you are not taking acidic anhydride, if you are directly adding CrO₃ and you are taking H3O+, so obviously this is a very strong oxidizing agent, so this will oxidize carbon into carboxylic acid. So if you need to convert toluene into benzoic acid, you can add CrO₃ in presence of H+. If you want to control the reaction till aldehyde, then you have to add acidic anhydride. So basically acidic anhydride is this molecule. Okay, so this is what acyl group is, this is what acyl group is. So that is why it is writing this as AC2O. Okay, so I hope this is clear to everyone. Now the next set of reaction through which we can prepare aldehydes and ketones, aromatic aldehydes and ketones, is electrophilic aromatic substitution. So we can carry out a Friedel-Crafts acylation reaction. We can carry out a Friedel-Crafts acylation reaction. So in a Friedel-Crafts acylation reaction, what we do is, we take a benzene, we treat benzene with acyl chloride and AlCl3. AlCl3 is basically a Lewis acid. It will pull out the Cl, it will form a acyl carbocation which will be attacked by benzene ring, and an electrophilic aromatic substitution reaction would happen and will form this particular molecule. If R is methyl over here, then it is known as acetophenone. If R is a phenyl ring, then it is known as benzophenone. Okay, so we can carry out a Friedel-Crafts acylation reaction to prepare a aromatic ketone. The next reaction that we can do is, this is known as Gaterman-Koch reaction. We can carry out a Gaterman-Koch reaction. Now what happens in a Gaterman-Koch reaction is, we take benzene and we react it with CO and HCl in presence of AlCl3 and we form benzaldehyde. So this is again an example of a electrophilic aromatic substitution reaction. What happens exactly in this reaction is, CO first reacts with HCl, so this reacts in solution in C2 and generates a formyl chloride. Formyl chloride upon reaction with AlCl3, AlCl3 basically abstract the chloride ion, it forms a formyl cation. Benzene attacks on the formyl cation and we get benzaldehyde as the product. So this is the same reaction that we have done in the electrophilic aromatic substitution reaction. Next reaction that we can carry out is Gaterman aldehyde reaction. So the next reaction is a Gaterman aldehyde reaction. Now in a Gaterman aldehyde reaction, we take benzene ring, we react it with HCN, mixture of HCN and HCl in presence of AlCl3, and again we get a benzaldehyde molecule. So again we get a molecule of benzaldehyde. Okay, so we react benzene with HCl HCN and HCl, and we get a molecule of benzaldehyde. So what is happening in this reaction is the cyanide first reacts with HCl. So this HCl is an acid, so it will leave a H plus ion. So this H plus ion will protonate the nitrogen. Okay, negative charge will be formed on the carbon, so it will form a molecule like this. So again AlCl3 will abstract the Cl. A cation will be generated at this point, at this particular carbon. Benzene will attack on it and it will form a imine. Now we know that imine on hydrolysis, imine on hydrolysis basically gives us aldehyde. So first it will form this particular cation which will be attacked by benzaldehyde. So it will, which will be attacked by a benzene ring. It will form a imine which upon hydrolysis will give us benzaldehyde. So these are the few important named reaction. Now there is one more reaction I think I missed out in alkene. Now this is known as Wacker's process. I think this is mentioned in NCERT as well. So Wacker's process is basically the oxidation of alkene in presence of PDCl2. PDCl2 basically acts as a catalyst. So if you take an alkene and you react it with O2 in presence of PDCl2, which is acting as a catalyst, so it forms aldehyde in this case. So if you are taking any alkene like this, suppose you are taking styrene, you are reacting with O2 in presence of PDCl2 and CuCl2. So in this case we form a ketone. So we form a acetophenone in this case. Okay, so this is an example of Wacker's process. Okay, so these are the few reactions through which we can prepare aldehydes and ketones. Okay, so I hope all the reactions are clear to you, and most of the reactions are connected with the idea or the concept of the previous chapter. All these reactions are basically previous chapter reactions. So this is electrophilic aromatic substitution reaction. This is a reaction of alkene. Okay, this was a new reaction. Itard reaction was a new reaction. Similarly, Stephen's reaction was a new reaction. Okay, so with organometallic we have already done this. Only thing was introduction of dibyl H. Rosenmund was a new one. Carboxylic, again this was from directly from your organometallic compounds. So this was a new reaction from carboxylic acid. Oxidation of alcohol we have already done. Alkylides, this was the same mechanism as that of Schwann oxidation, easy to remember. Similarly, from alkynes or from alkenes, right, they were repeated reactions that we have done in the hydrocarbon chapter. So if you look at the chapter, this preparation, I am talking about preparation, doesn't have much of a reaction. Most of the reactions are repeated one. So when you are doing these reactions, ensure that you are also revising whatever you did in your 11th class, so that all the hydrocarbon portion is revised as well. Because once we complete organic chemistry, only thing that needs to be done is GOC again. Okay, so you need to revise GOC, general organic chemistry, only because we have talked about all the chapters, we have talked about isomerism as well. So you need to just revise your GOC, and that will complete the organic chemistry fully. Similar is with the physical chemistry. We have done all the chapters of physical chemistry of 12th class. So after after the month of November, you just start revising your 11th class portion as well, so that by the end of December you are able to complete the entire syllabus. The only thing that is left is now inorganic, so don't worry about inorganic. Inorganic is mostly theoretical, so you need to spend a lot of time in revising, in memorizing things. We have done coordination chemistry, that was a very important portion, but that was little logical and conceptual, easy to remember, but the rest of the chapter that follows in inorganic is purely theoretical one, so you need to remember those chapters. Okay, so this is it for today. So I hope you will practice these reactions again, you will memorize these reactions again. So this is it for today. So this is Animesh signing off for now. We'll catch in next lecture with some important chemical properties and chemical reactions of aldehydes and ketones.